My name is Makayo Kure. I'm an associate professor in the Department of Mechanical Engineering at the College of Engineering, Design, Art and Technology of Makerere University. In that position, I offer graduate courses in bioenergy and design of thermal systems, among others. I would like to welcome you to this presentation on the topic of burning and gasification of biomass. We will start with a few principles. When a substance burns, we say it combusts. So I'll be using burning and combustion simultaneously. Burning or combustion is a rapid reaction between a substance and oxygen that releases heat and light. A fuel in that is then a substance that reacts with oxygen under high temperature conditions to release useful energy. Now, fuels contain hydrogen and carbon. That's why sometimes they are called hydrocarbons, which, when each of these substances burn, turn into carbon dioxide and water and release a large amount of energy. Actually, the energy in the biomass is from the sun, which is converted to chemical energy through photosynthesis. Subsequently, when a person burns dried plants or wood to produce energy in the form of heat and light, he or she is releasing the sun's energy originally stored in that plant or in that wood through photosynthesis. To bring this home in our area here in sub-Saharan Africa, we need to note that most of the energy used in the households, in commercial places, even industries, comes mostly from biomass. Another principle to note is that plenty of air is needed to provide enough oxygen for a fuel to burn completely. Oxygen must be provided in excess to ensure complete combustion of the fuel. Plenty of oxygen is required to ensure complete combustion, i.e. eliminate incomplete combustion and maximize heat generation. If there is a shortage of fuel, of air, oxygen in this case, incomplete combustion of fuel takes place. So instead of producing carbon dioxide and water, incomplete combustion produces carbon monoxide and even particles of carbon soot, also known as smoke. This incomplete combustion also releases less energy than complete combustion. If you have a piece of wood which you want to burn, you need to put it under conditions that it will start the fire. So for the wood to catch fire, there must be a number of things. You need oxygen, and you need some initial heat source that to raise the temperature that will sustain combustion. Otherwise, if the temperature is low, the fire dies. Let's talk about what exactly happens when a piece of wood catches fire. It goes through a number of processes. One, when wood gets hot, it releases some gases, and these are termed volatiles because they evaporate. These volatiles may then burn if there is sufficient oxygen and temperature. Now, not all wood vaporizes. A good portion remains. This part which remains is a solid carbon black material, technically called char. or simply charcoal in common language. The third process is that some of the radiant heat from the flame strikes the wood. I'm talking about the flame that comes out of burning of the gases which have evaporated from the wood. So that flame is hot. It's hotter than the wood. So some of that heat is radiated back to the wood, which causes further decomposition. Hence, it maintains the cycle and the fire keeps burning. The gases can be released at about 200 to 300 degrees Celsius or centigrade, but complete combustion takes place at about 650 degrees or more. The next process is that when there is complete combustion, the region where the combustion takes place emits light and is seen as a flame. Complete combustion leads to a blue or colorless flame. If the gases from the wood are unburned, they escape as smoke, as I said earlier. And of course, smoke is wasted energy. So in summary, the lesson we take is that the general combustion process of a solid biomass, the general combustion process of a solid biomass includes drying, that is evaporation of water from the wood if the wood is wet. So in summary, we note that the general combustion process of a solid biomass includes drying, that is evaporation of water from the wood when the wood is wet, and normally it's not as dry as one thinks. Then breakdown into an evaporation of gaseous molecules called technically pyrolysis, combustion of these volatiles, and oxidation of the char. If the volatiles are released from the wood and the char is not combusted, then we remain with charcoal. And this, as we have seen, can be used subsequently as a fuel also by supplying oxygen or air. And this can take place in another place altogether, so you can transport the char alone. Smoke from wood burning is made up of a complex mixture of gases and fine particles, also called particle pollution or particulate matter, abbreviated simply as PM. In addition to particle pollution, wood smoke also contains several toxic air pollutants. Paradoxically, smoke may smell good, especially on food, but itself is not good for us or for you. The biggest health threat from smoke is from fine particles. These microscopic particles can get into a person's eyes and respiratory system, where they can cause maladies like burning eyes, runny nose, other illnesses such as bronchitis. These fine particles can also make asthma symptoms worse and trigger asthma attacks. If this happens indoors, the effects are even more severe. Therefore, we have to be very careful in burning wood or biomass indoors. And we have to ensure that the equipment and the process we use releases as little smoke as possible. Finally, among the principles, when the char is burnt, there remains a residue called ash. ash is actually an impurity that will not burn. Or if it burns, it still remains, some residue still remains. And this is typically in the range of 5 to 40% of the biomass. Ash is important because you need to handle it. After you have got the energy from the wood, you have to get rid of the ash. It also causes problems with the equipment. So you need to design the equipment to burn wood or biomass such that you are able to remove biomass. In terms of measuring the amount of energy per kilogram of biomass, you can see that if there is a percentage of it which will not burn, already you are losing that percentage of heat. So it reduces the total amount of heat that you get from a kilo of biomass because there is a presence of ash. Next, something about gas burning. It turns out that gas fuels are the most convenient because they are easier to mix with oxygen. Because when you have a solid biomass, the oxygen has to diffuse to pass through the ash sometimes, and so you don't get enough of it into the wood. But when you have a gaseous fuel, it's very easy to quickly mix, and so you achieve good mixing with oxygen, you achieve faster mixing, and then the burning is much better, and so you can normally get a blue flame when you are burning gas. So this principle is utilized in trying to improve the amount of energy that we can achieve from wood by turning the solid wood into a gaseous fuel. And then we burn the fuel because we find that there are several advantages, as I said, with the gaseous fuels. They are easier to hold, to handle. The burning systems are easier because you need to mix the gas together with the oxygen. There are also environmental benefits because you reduce on the emissions when you burn a gaseous fuel. So one such gaseous fuel is the one which can be derived from waste, biomass, or wood. So we're going to spend the next few minutes talking about biomass gasification with that short background. So technically, biomass gasification is the transfer of the energy content of a solid fuel into a gaseous energy carrier. So we said the resulting biofuel or gas is easy to clean and transport and can be combusted in different engines, such as gas turbines or modified diesel engines, as well as furnaces and fuel cells. So this provides us a way of converting a solid biomass into electricity without having to go through a different process, a more complicated process that sometimes involves boiling water, getting steam, and using steam in a steam turbine. So we can go straight from the gasified wood to a diesel engine. So what is the difference between gasification and burning that I earlier on talked about? There is a small difference. The small difference is that we need a smaller amount of oxygen than we require for complete combustion. So you supply the biomass or wood with a smaller amount of oxygen or air so that you don't get complete combustion. Instead, what you do is that you get the volatiles from the wood, you capture those, and you use those for subsequent combustion. So in other words, a simplified scheme of gasification involves feeding the fuel into a reactor that we shall call a gasifier. So you feed this fuel via a relatively airtight closure. You convert the fuel into a producer gas. Then you take the gas through the process, and eventually you turn the gas into another fuel. The gases that come out of this process include carbon monoxide, hydrogen, methane, carbon dioxide, and other substances that are extracted out of this gasifier or reactor. And these are then directed to what we shall call downstream devices that I've said could be a gas engine for conversion of the producer gas into power. In principle, I can say that any biomass can be gasified. Wood, waste wood, crop residues, municipal solid waste, to name a few. However, there is a caveat to that. The major characteristics to watch for in order for the process to be efficient and effective are the amount of moisture in the biomass. It should be around 20% for some gasifiers and a little bit more for others. I mean, other gasifiers can accommodate moisture contents slightly more than 20%. The size of the biomass should not be too small and not too big, generally ranging between 50 millimeter piece to 200 millimeter piece. The ash content, as I said before, should not be more than 6%, otherwise we have problems in that. And of course, we have to worry about the percentage of fine particles in the whole biomass. If you have very fine particles, a large percentage of fine particles, then you have problems, as I will describe later on the gasification process. So in principle, we can gasify any biomass, but we have to be aware of those final four principles: the moisture content, the size of the biomass, the ash content, and the percentage of fine particles should not be more than 15% in the whole heap. The gasification of biomass with the downstream gas engine conversion of the producer gas into power and heat, of course, offers a technical possibility for the provision of combined heat and power from renewable energy sources, notably solid biomass. It's particularly useful in areas of decentralized utilization of biomass, such as areas which are far away from the grid, but they will have to have certain conditions. And one of those challenges are that you need a sufficient supply of biomass feedstock. And of course, unless produced on a renewable basis, this can become a problem for the community. So areas where we have introduced this technology for our rural community are those areas where we have identified that they have sufficient and abundant renewable sources of biomass. Another challenge is the quality of fuel. I said earlier on that the fuel must be within certain conditions. So those conditions need to be controlled a little bit, and if you cannot control them, then you need to do something. You need to pre-process the biomass into those uniform conditions so that you can have a higher yield of gas, and therefore you can achieve an efficient and productive process. The other challenge is the producer gas leaves the reactor with a number of pollutants and at a high temperature. Now, the third challenge is the producer gas leaves the reactor with a number of pollutants. And also it's at high temperature because this process takes place at temperatures ranging between 700 to 1000 degrees Celsius. So in the subsequent steps, the process of obtaining heat from this gas and also using it in an engine, we need to clean, cool the producer gas. So that adds onto the process. So therefore, it complicates the process, which makes it a little bit difficult to operate as well. Adding on to that, the fourth challenge is that gasification is a complex process involving thermal and chemical processes operated at ambient or increased pressure. So outside you have the ambient conditions, but inside the reactor you have very high temperatures and also sometimes you have high pressure. So for thermochemical conversion, it's necessary to supply sufficient solid biomass and gasification media, or air for that matter, as well as to provide a pressure and temperature regime by means of suitable gas control and geometrical construction of the reactor. So design and subsequent operation need highly developed skills. Now, fifth challenge is that individual fuels and gasifiers and process steps and modes of operation in those steps, as well as a number of other important points, must be taken into consideration. Non-observance of these points may entail negative effects on the normal operation of the gasification plant and also possible hazardous situations. Talking about hazardous situations, producer gas contains carbon monoxide. Carbon monoxide is a poisonous gas, principally because it reduces the ability of blood to carry oxygen. So the operation of a gasifier requires adequate precautions. Environmental effects is the next challenge, because biomass gasification takes place in an explosive mixture of toxic and combustible gases, and also amounts of residual substances in combination with gas production and gas cleaning are produced, extracted, converted and recycled. And this leads to pollutants and effluent. And this can be a problem for operators because they need to protect health and the environment, and therefore suitable requirements must be set regarding the technical equipment of such facilities. In summary, from what I've said about gasifiers, gasification is a good process. It's a process that enables us to use biomass available almost in any area or in any region for purposes of providing electricity access, as well as conveniently controllable heating. However, the plant itself is complex and one needs to prepare adequately in terms of the design of the plant, in terms of setting it up, in terms of training operators, and in terms of managing its human and environmental effects. With the economic benefits of getting electricity access using solid biomass, it's possible to overcome some of these challenges. So If one is interested in setting up such a gasification plant in an area, it's important to look at quite a number of these points that I've raised to ensure that the plant works effectively. I would like to take this opportunity to thank you very much for your patience and your attention.